Next theorem that we are going to see is countable union of countable sets is countable. In the statement, the word countable is there for many number of times. Okay, let us try to understand what is given in the statement. Countable union, which means we are going to make a union like this. Okay, we are going to perform some union like this. Okay, countable sets. Countable union of countable sets, which means all those sets to which we make the union are going to be countable. Okay, and finally what we have to prove, this union, suppose if we take this union to be yes, this is also countable. This is what we need to prove in this theorem. Okay, so in this theorem what are we going to prove? We are going to take a collection of countable sets and we are going to make the countable union, and the countable union is also countable. This is what we need to prove. Okay, the same idea, the sequence. Okay, here assume that I am not going to write all those things. Assume that E1, E2, etc., En and etc. are going to be the countable sets, and the countable union of these sets is denoted as S. Okay, since each set is countable here, so let me write the elements of E1 to be x11, x12, x13, and it is going like this. Okay, the elements of E2 to be x21, x22, and it is going like this. Okay, in this way we will have elements like this, right? So this is x11, x12, x13, x14, and it is going this way. x21, x22, x23, x24, and it is going this way. Okay, here we are going to give some array arrangement to these elements. This way we have considered some array arrangements. Okay, these are all elements of corresponding E1, E2, E3, E4, etc. We have made the union of all such E's, and that is denoted as S. Now we know that all these E1, E2, E3, E4, when we look at these sets separately, all these are countable. We need to prove S is countable. So we are going to give the arrangement of elements in X. That arrangement is going to be done using this thing. Okay, just draw an arrow like this. Okay, as indicated by the arrows, consider the elements in S. x41, x32, x23, x14, and it is going this way, right? So this is how we have found the elements. Okay, now if we prove this is in some sequence, okay, we can say that this is also countable, right? Okay, by saying E1 is a countable set, what we mean, the elements are distinct. Okay, and this can be arranged in a sequence. But when we make union of all these countable sets, we do not have the guarantee that all these elements has to be distinct, because some element in E1, that for example I am saying, if I have some x17, this may be same as that of x429. Okay, this and this may be same. Okay, in that case, if suppose there may be many or few elements of this kind, okay, if there are anything, that is if there is some repetition, okay, here I have told you x17 may be equal to x429, and this may be same as that of in E127, x127 1, these three may be same. Okay, it is not mandatory that, it is not necessary that it has to repeat only once. It may be repeated for any number of times. If there are any such repetitions, we are going to omit the repetitions, and that will be counted only once. Okay, So when we make such arrows, suppose this x11 is same as that of x23, we will not write x23 here. Okay, we will leave that x23. As of now, for the notation purpose, I am just considering after omitting the repetition, I am writing like this. Okay, if that is repeated, I will not write that there. Okay, now I am going to make a mapping. Okay, of course we have to make some mapping. Okay, from J to S or S to J. Here I am not going to make a mapping from S to J. I am just going to make a mapping from S to T, where T is a subset of J. Why here we are making we are taking the subset of J instead of taking J? Because if we have to take J, we have to make sure that the 1, 1 and R2 has to be there. Okay, since there may be repetitions, I have told you this x11 and x23. Suppose if these two are same, we will not write that. So this place has to be there. As we have written here, this is 1, this is 2, and this is 3, 4, 5, 6, 7, 8, 9. So which means in this association, I will map x23 to 9. Okay, but this x23 is same as that of x11 as of now for this example purpose. F of x11 is 1. Okay, a same element is being mapped with two different elements. In that case, the mapping may not be well defined. Okay, that is why in this case, I will omit this 9 in this T. Okay, I am not considering the entire J. In J, I omit 9. So this becomes a subset. Okay. Similarly, if I have more than that also, I will omit those things in T. Okay. I will omit those things from J and I consider the rest of the elements to be the elements of T. Okay. As of now, okay, just have like this. Now, with this, okay, we have to associate something. Okay. This x11 has to be mapped with 1. How do we achieve it? Just think for it. Okay, we have 1, 1. So 1 into 1 is 1. Okay, 1 plus 1 upon 2 is 1. 1 power 1 is 1. So there are some ways to achieve the association of 1, 1 with 1. Okay, try for 2 into 1. Okay, so 2 into 1 is 2. Okay, fine. 2 power 1 is 2, but this 2 plus 1 upon 2 does not work there. Okay, come to this 1, 2. With the help of 1 and 2, I have to bring 3. If I add 1 plus 2, that is 3. Okay, for looking at this thing, this and this was the common in the first two things. Whereas in the third, it is not working. So, these cannot be some generalizations. Okay, we have to look for some other alternative. So, this is not going to work because if it has to go either for odd numbers, this is the case, and for even numbers, this is the case, but it is not coming like that. Okay, for the first and second case, we get something, they are common in both the things. When we go for the third, it is not working so. Okay, let me try another way. Okay, what happens? Okay, suppose the general case, let me write xnk. Okay, what happens? 1 plus 1 minus 1. Right, 1 plus 1 minus 1. Here it is both are same. Okay, so it is going to be the case. So this is simply 1. Okay, suppose if I consider 2, this becomes what? This is 1 and this is 0. Okay, if I simply add 1, I get it, right? Okay, let me come here. 2 plus 1 minus 1. 2 plus 1 minus 2. This is going to be 2 into 1. I am getting 2. Here I am getting 1. When I add 1, I get 1 here. When I simply perform this, I get 2 here. Okay, let me come to the third one. So it is 1 plus 2 minus 1 into 1 plus 2 minus 2. This is going to be 2 times of 1, which I am getting only 2. But I have to get 3. Okay, let me add 1. So I get 3. Okay, as of now, this is kind of going good, right? Okay, let me go for this case. So 3 plus, if I get 4 by simply this, I am going good. Okay, 3 plus 1 minus 1, 3 plus 1 minus 2. So this is 3 times of 2, which is 6. I am not getting 4, I am getting 6. Okay, let us try to make some alterations in this. Let me divide this by 2 and add 1. What happens here? I am going to get 1. Okay, divide this by 2 plus 1. I am getting 2. Good. Okay. Here, divide this by 2. But if I add 1, I am getting 2, not 3, right? So here must be something else. Okay, let me add 2. I am getting 3. Okay, what? So I am going to get 3. But if I add only 1 there, I will get 4. Okay, I must not add 2. So if you just combine all these things and compare here, this is n, k. Okay, so both these are same. So as of now, don't go for this. Come to this. This is n and k. So when I add the k value, I am getting 2. Okay. In this case, it is 1, 2 when I add 2. So when I add the k value, I am getting 3. Similarly, let me try here. Okay. So this is my k value. So when I add 1, I am going to get 3 plus 1, which is 4. Okay, fine. Let me try for this x32. Okay, x32. Let me erase this part. x32. Let me try for this. I have to associate this with 8, right? So 3 plus 2 minus 1. 3 plus 2 minus 2 upon 2, and this is 2. Okay. So this is 5 minus 1 is 4, and this is simply 3 upon 2 plus 2. So it is going to be 6 plus 2. I am getting 8. Good. Okay, let me go for x14. So it is 1 plus 4 minus 1, 1 plus 4 minus 2 upon 2 plus 4. So this is going to be 4 and 3 upon 2 plus 4. It is 6 plus 4, which is 10. So it is working perfectly fine, right? So here we need to make the generalization. Okay, what we have actually done, what we have done is n plus k minus 1, n plus k minus 2 upon 2, and we add k to it. Okay, so if you define a mapping like this, okay, suppose you do not have x23 here, that will not be mapped with 9 by this means. Okay, so this mapping is going to be a 1 1 and onto between a subset of subset of j. So f is 1 1 and onto between s and a subset of j. So this tells you your s is at most countable. Okay, at most countable means s is either finite or countable. You are left with these two possibilities. If you prove it cannot be finite, you can tell that it is countable. Okay, look at this. What is S? It is union of countable sets. Okay, what are the countable sets? These are all the countable sets. In this, E1 is infinite set, right? E2 is also infinite set. All these are infinite sets, right? Even though you are removing some terms, you are not going to remove many such terms, right? And there are infinite number of sets like this. Even if you take only one element from each set, it is going to be infinite. So it cannot be finite. Okay, since all the elements in the union are infinite, okay, your S is not finite. So if F is not finite, you are left with only possibility that S is countable. Okay, that's it about this theorem. The main thing that you have to always remember is that what does that countability means? Why are we taking the subset of J here? Okay, so you have to consider this. You have to consider this arrangements. This is what going to help you in arranging the elements in S, and using that you are going to define a mapping. And once you are able to associate x11 with 1, x21 with 2, x12 with 3, by the definition itself you can easily see that this mapping is turning 1, 1 and on2 between S and T. Okay, the reason for choosing this T, that is a subset of J here, is we omit the repetitions. Okay.